We will talk towards the end of this hour about random forest. And yet it's not been popular with some corners of the community for a long time. And if you switch to the screen, I think I can give you a bit of a reason for that. So this is a technical report from Biao, and he writes that although the mechanism appears simple, it involves many different driving forces which make it difficult to analyze. And in fact, the mathematical properties remain largely unknown to date. And in particular here, he's studying the consistency of random forest, and he says that most theoretical studies have concentrated on isolated parts or stylized versions of the algorithm. So random forest and all its colleagues, these methods, at least as they have been presented, are not probabilistic or Bayesian. They do not follow from deep principles, at least to the extent that they have been understood today. And yet they're some of the empirically most successful methods around. So I will tell you some of the heuristics and the math that goes into analyzing these methods is extremely complicated, and yet usually does not make statements about the exact algorithm. So like this introduction here says, these difficult proofs, they allow statements about algorithms that are similar to, but they are not quite the thing. And a very influential person in this whole field has been Leo Breiman, who died in a few years ago. I think it was 2005. And well, he was actually a very humorous person. And if you have time, then luckily he's preserved on some video lectures. You can see him in person. And well, I think this is the kind of thing that brings out his sense of humor. So he proving this was easier for him than looking up, where it has been proven before, if at all. And he was a mathematical statistician first, and then worked as a consultant out in the wild, and then eventually came back to university to work in an area which nowadays would be called machine learning. And he was a bit special in the sense that he, I think, was a very lucky union of well, qualitative arguing and qualitative insight, and then tough math. So he mastered both, and he strongly believed that you needed both, the intuition and the math. And that put him apart from many of his colleagues who have either one or the other. And he was also instrumental in developing the classification and regression trees, which is the first algorithm and building block that I want to present. These are abbreviated as CART. And such classification and regression trees use a series of simple, typically yes or no questions to classify a sample. And this classifier can then be represented as a, if you just asked yes or no questions, as a binary tree. So you would start, let's say that we have just two features, x1 and x2. And we want to construct a decision boundary here, then we could ask at first if x1 is larger than some threshold c1, and that will give you a first split of your feature space. and then the answer maybe no or maybe yes. And let's say we want to further partition here, then we could ask if x2 is greater than some value c2. And now this will give us a partition that's important, not across all of feature space, but we only ask this question contingent on the answer of the first. So only if we answer the first question with yes, so only if x1 was larger than c1, do we get to see that second question at all. Okay, so it's important that this second split does not go across all of feature space, but only across this subspace here. And well, this nesting property is encoded in the tree. So we can ask, or the answers could be no or yes. And so if x2 was smaller than c2, then I can answer another question. I could ask again if x1 is greater than some parameter c3, for instance, corresponding to this partition here. And let's say we want to stop here. And in these leaves, we have to, okay, let me do one more. Let's say x1 is smaller than c3. Let's do a final split here at some value c4, which would be this one here. Now, this is a binary tree. This is the root. And these entities here are called the leaves of a tree. And now we can say in each leaf what should be the class. So let's say we want class 2 here and class 1 there. So I would have class 1 here and there, and the rest would be class 2. So this was just to illustrate the correspondence between the tree and the partitioning of feature space. And you can see that each node of the tree corresponds to one of these regions in feature space. And this tessellation of feature space will, of course, remind you of perceptrons and all that. Now, the question is, how do you get this partitioning? Of course, in the real world, we start with a data set. So let's say we have samples from class 1 and samples from, looks like the measles here. So class 1 is red, class 2 is green. Typically, we're given these samples first, and we want to construct the tree from it. But now you could come up with all kinds of criteria. You could, for instance, say, we want the tree with the smallest number of nodes that will partition my samples, or something like that. But it turns out that such global objective functions are very hard to optimize. And people instead revert to, and that very successfully, to greedy strategies. In particular, for such a classification and regression tree, you can iteratively, in constructing the tree, ask that question that reduces the impurity of a node most. So because it's greedy, the resulting tree is typically, for example, not of minimum size or has no other of these globally optimal properties. Now this leaves you lots of freedom in defining your impurity criterion, and indeed people have used different things. So if you want to build a regression tree, for instance, this could be the spread from your estimated value, but here I want to focus on classification. And well, there are three famous ones. There's the entropy, where the impurity I of a node n this notation is not very pretty, and the letters now mean different things from when we talked about SVMs. So Wj would be sorry, this would be simply class J, and P of Wj would be the fraction of patterns or of observations in class J. And this is a node of a tree, and I'm writing I for the impurity. And if we just have two classes, then should have looked, no, I just wanted to secretly look up the precise shape, but it's something like that. So the entropy is maximal if we have a chaotic mixture of both classes, and the entropy becomes minimal if we have just members of the one or of the other class in there. Then there is the misclassification impurity, which for two classes is just that. And I have rescaled these curves here to have the same maximum. And finally there is, and this is what's most frequently used, there is the Genie impurity. Which is an inverted parabola, as you will see in a moment. And the motivation for this one here is this is the expected error if you randomly pick a sample and predict the class of the entire node based on that. So you see, P of Wi gives you the probability of selecting a sample from class 1 or 2 or 3 or 4. And then the sum over the second term is the probability that you make a wrong statement. So the structure of the sentence would be more clearly reflected if I wrote it as follows. Okay, and it turns out that you can express that as 1 minus the sum of the squared probabilities the reason is that if we multiply the sum over all probabilities, so this is 1, if we write 1 times 1, we get 1, and I can rewrite that as the non-diagonal terms plus the diagonal term. And if you now, well, if you bring this on the other side, we're left with Genie impurity. By the way, this was proposed in the, we'll come back to the formulas in a moment. This was proposed in the context of sociology and has here been used to measure the income disparity. And actually it has been reinvented a few times and it runs under different names, but people in the social sciences know what it is. So what this plot tells you is that in Brazil you have a few very rich and then many very poor people, and then there are states like Scandinavia in particular, or in times when still everyone was poor in certain countries, that made for a low income disparity or low Gini index. Okay. So, and you can now use any of these impurity criteria here to construct your tree. Yes? Yes. It's exactly. Yeah. You can now use any of these impurity criteria to construct your tree. And what you do is that you measure the merit or the attractiveness of splitting a node Yeah, no, a node is so leaves are the end or are the final nodes. So a node could be any of these internal vertices of the tree, and leaves are the final nodes. So you can measure the attractiveness of splitting a node into a left and a right child by taking, say, the impurity of the node minus the fraction of patterns that go into the left child times the impurity of the left child. And then we have the fraction of patterns that go into the right node times the impurity of the right child. Okay, so these are the impurities of the children. And these are the fraction of samples or of training data that go into the left or into the right node. Now about these splits, in most cases, these splits are based on a single feature, and that's a pretty drastic simplification to make. So graphically, the example that I showed before that gave you such a split in terms of axis orthogonal planes, but you could in principle take any kind of split. You could build oblique splits if that is a better fit for your training data. But that has not been investigated so much. So such trees are also called monothetic trees, and that you could call an oblique tree or a tree with oblique splits. So there's the recipe. Then we can look at the cost of this. How about the computational complexity? So can you tell me what we have to do at the root node? Exactly. And so in terms of more atomic operations, what does that mean? Mm-hmm. Yeah. But to do that effectively, because we always need to know how many go into the right and left child, to do that effectively, it's good to sort the samples first. So we sort our n samples from the training set, which gives us a cost if these are continuous features. if I have a discrete set of levels for the features, I could use linear complexity sorting algorithms, but for continuous features, let's say this is n log n complexity. And we want to do this according to each of the p features that we have. So overall, this gives me p times n log n. And then for each possible split, I want to compute the impurity. I have a total of n minus 1 possible splits if I want always at least one observation going into each child. And we also want to do that in all the p dimensions. So that's order n times p. So that overall at the root node, this is our complexity. Now, for the children, we don't know exactly how many observations will go into one child and into the other child. Averaging across all data sets, we will find that each child receives half the samples, but that need not be so in practice or in a single tree. And in the next level, there are twice as many nodes. So we get for, if we call the root node level 0, then I would get at level 1, the number of dimensions is still the same, so p times, but now I have approximately half my number of samples, so n half log n half. This was for the left child, this was for the right child. Okay, and then at level 2, using the same argument, you will find that you have p n log n over 4, and so on. Now, if you have a balanced tree, then this will have of the order of log n well, for a balanced tree, we would have exactly log n levels. But again, there is no guarantee, or we cannot assume that our tree will be balanced. But if we assume it for now, then we would have log n for the number of levels times this complexity that we've seen in each single level. So that we get overall p n log n squared. So that is very cheap. It's about as cheap as the training of any classifier can get. It's linear in the features, it's linear in your number of samples, and log n is not much. This was only a very approximate calculation because we cannot assume that the trees are balanced.
So at each node we ask the question which feature is most effective for division for the decision.
Yes. So at each, in general, you have many more than just the two features that I showed here. And at each node, you can ask for classification and regression trees. You will check any of the features and see which one reduces your impurity most. Mm-hmm. Oh, yes. Well, if you want your tree to be a perfect fit to the training data, then you may need to build a very big tree. But this will be an overfitting to your training data. And you're right in that sense, that if you want to use a single tree, then you should not overfit to your data. So you should either stop the growing procedure at some point, or you should grow it out full and then start pruning it back. Okay, then I didn't get your question. Ah. I'm trying to show you but not yet, Bernhard, but I'm trying to show you some code which illustrates, I think, your question. Oh, MATLAB crashed. I'm trying to see if this is your question. I have here computed this reduction in impurity for the following data set. I have a one-dimensional, well, I always split along one feature, so I project onto the single dimension. And here I have features, I took P for the positive class and N for the negative class. And I think your question was, if I now compute this reduction in impurity, if I cannot stop roughly halfway down. And no, you can't, because it really depends on how your, you see how your data is distributed. Yeah. So here's an example where, it first looked like probably the positive class is left and the negative class is on the right. So this would be a good point to split. But then you go further and you see, oops, there's much more of the positive class here, and it's actually a better idea to split over here. So you have to try out all n minus 1. You see these points here, which I've connected by the blue line. They're always evaluated in the middle between two of the sorted observations. Okay, and this plot already shows you, well, another thing which is clear by design, that if you use these monothetic splits, then you're invariant to scaling of your axis, which is a nice thing. If you remember the discussions we had about, the k-nearest neighbors, for instance, and how it was important to scale the two axes in a similar fashion. Here, I can, take the log or the exponential or whatever of this axis, and it will not change the pattern of the maxima. The maxima will stay in the same place. Okay. So if we did use just a single tree, which you shouldn't, then we would need to regularize it. Without, you are very likely to overfit, and hence there are a couple of possibilities. One would be a so-called early stopping. So in this case, you abort extension of your tree if the impurity reduction is too small. And well, building trees is a greedy strategy, but early stopping is a greedy strategy on top of that. Let me use the XOR problem as an example. So let's say we have the green class and we have the red class. And if you now ask if you will get any significant impurity reduction by splitting along your feature number 1 or by splitting along your feature number 2, you will see that none of the axes taken by itself is informative. So what you have to do is to at first do a split, which doesn't help much, but conditional or given this first split, you will be able to make more sense of your data. And if things look totally uninformative, you could, for instance, just split on the median or something. Yeah. So early stopping is a greedy procedure. Or you could do early stopping based on cross-validation. That would already be better. Or you could do early stopping if there are too few samples left in a node. Or you could do an early stopping when the sum of your impurities, the sum over all nodes of your impurities, plus some parameter times the tree size no longer decreases. Now the problems with these approaches are that we have these parameters that we need to choose. So the choice of the parameters, and the other problem is the horizon effect. So in this example, this first split is not going to reduce your impurity at all. But once you have this split, you can now make a very profitable second split, and so on. So the horizon effect means that you should invest and wander through the valley of fear or drought or whatever your preferred metaphor. To deal with this horizon effect, a better strategy is to use pruning. So it means you first grow the complete tree until you have pure leaves, and then start cutting back stopping according to some criterion. So, what are the problems with CART? There are a few. One is that we have low bias, so we can fit any decision boundary that we like, but we have extremely high variance. And this is something that you should try out in the exercises. So if you take your training set, you will get one tree, and if you perturb your training set ever so slightly, you will get a completely different tree, and so on. And that's quite confusing. Unless you regularize in some appropriate fashion. And secondly, at least if you use these monothetic splits, they have difficulty with correlated data. So I have a picture here, courtesy of Björn Menze. This would be benign, where with a few splits or a not so complicated tree, you can get pretty far in telling your classes apart. But if your data is strongly correlated, your two classes are strongly correlated, you will tend to build very deep trees. So, and that was where the story ended for 10 years or so. And then came random forests, and everything was good. So I will start with a list of selling points. That sounds like I'm getting paid for this, which I don't. The most important one, perhaps, is that empirically you get very high performance without parameter tuning. So it has two parameters, but it turns out that performance is not very sensitive to the choice of these parameters, and there's a rule of thumb on how to choose these or how to set these, and typically the rule of thumb works well. This is in stark contrast to SVMs, where typically you need to do something like a grid search to optimize your parameters. Then it deals well with both categorical and continuous data. Sorry, categorical and continuous data. It is fast in training, and it is fast in prediction. In prediction especially. So remember, the depth of these trees is only of the order of log n. So you only have to answer of the order of log n questions. Oh, handles. This is, yeah, plays nicely with categorical and continuous features. So again, assuming the balance of the trees, which is not given in real life, this would be roughly of the order of log n yes or no questions that you have to answer. So it's few questions, and the questions are cheap to answer because you only need to access single features. Then, like cards themselves, it is invariant with respect to scaling of features. And it has means to compute a feature importance. So telling you which features are relevant and which are not. And finally, it also has an inbuilt estimate of the generalization error. So all of this is great. On the downside, at least mathematically, the thing is still ill understood, especially why it works so well. So there's space for you if you want to have a career here in science. Now, I've started with all the good properties and have not told you at all how it works. It merges two important ideas. On the one hand, bagging, which is a shortcut for bootstrap aggregation. And I will say what bootstrap is in a moment. And on the other hand, random split selection. So this was proposed by Breiman. And this was proposed by Dieterich. And it turns out that you need both. Leaving away one or the other does not give you nearly the same good performance in the same. So what does bagging do for you? So bagging means is that you construct multiple training sets by sampling from the original training set with replacement. Though I think that sampling without replacement would actually be fine also, at least if you have enough data. And this has the effect of reducing the variance of the ensemble. So the individual trees will all look different, but since you average over many of them, you get out a decision boundary that is smooth and that will not change very much if you get to work on a second training set from the same source. So this leads to a smoother decision boundary. And secondly, so what you do is you build these multiple training sets, you train a tree or you construct a tree on each one of them, and you then pool the decisions. Now in the tree construction I use these random splits, which means I should say first that we construct one tree per bootstrap training set. Yes. So you have an urn holding your original training observations, and now you, without looking, let's say there were 6 samples in there. You now take 6 samples, but you put them back each time. So it could happen that you select the first one. In the extreme case, it could happen that you select the same observation 6 times, but it's never going to happen. Well, it's not very likely. Huh? So this is what with replacement means. Okay. So you construct one tree per bootstrap training set, and all these trees together constitute an ensemble. So taken together, that gives you an ensemble. Now in this tree construction, this is where these random splits come in. At each node, when you ask yourself where you should split or along which feature you should split, you consider only a subset of all features, a random subset. And this second source of randomness is important because it makes the tree construction a little less greedy. You see, if there is a variable which by itself would not have been selected because it's a little bit weaker than another one, if you now use random subsets, it can happen that the seemingly more strongly predicting variable is left out, is not considered, and then this weaker variable has a chance to get in. And it could be that this weaker variable in conjunction with other seemingly weak variables actually is very predictive. So it allows you to find interactions between variables.
Random means that at each and every node it's random on the whole tree.
Exactly. So you pick a different random subset at each node. So it, let me say, it gives seemingly weak features a chance to get into the tree. Yeah? And it's now very technical, very non-technical the way I'm expressing it, and to become helpful in conjunction with other variables. All right, and by the way, these samples, when you've sampled with replacement, you also get a few samples that you do not select for your bootstrap training set. And these can be collected. This is your out-of-bag data set, which can be used to estimate the generalization error of your classifier. And I want to show you in pictures what it does. So here are these training sets have been created with resampling, and you see that each of these bootstrap training sets gives you a different classifier, and you do that 200 or 300 times, and then you average over all your predictions. So you pool the decisions from all of your individual decision trees. And that gives you then on the one hand values between 0 and 1, which however unfortunately cannot directly be interpreted as a posterior probability, even though many people use it as a proxy for just that. And it also gives you a decision boundary, an overall decision boundary, And it turns out that while the individual trees are totally unstable, they have a high variance, this averaging over many trees gives you a decision boundary that is actually very stable. So we have these two sources of randomness. One comes from the bootstrap training sets. The other comes from this use of subsets of features. And taken together, they make for a very, very strong classifier. And well, there are papers that compare empirically across many training sets how well they work. And these papers show that on average you get very high performance out of the box without tweaking anything in these classifiers. And I'm starting to see them more in computer vision now. So people really loved support vector machines, and you know, they have all this nice math and so on, and have stuck with this for a long time. And they're now starting to use random forest a lot because it's so fast to train, and well, working very well empirically. And I'm curious to see, you know, if the whole field will convert, or if they're or if we see new developments. So I didn't have time today to talk about how to compute the feature importance, and I will add that as a postscript next time, and will also show you a couple of examples where random forest is used to great success. Thank you.